Here I'm going to briefly overview chemical reactors and describe 4 types of ideal reactors and indicate a few important aspects. And so what we're looking at is where we have reactants A and B entering the reactor, and this is in this case a flow reactor, and we have A and B that have not reacted leaving, and then 2 products D and U. And the situation we're looking at is if we were to have 2 reactions, A plus B going to D, A plus 2B going to U. And the important thing here is this is the desired product that we want to make. And an example might be we're looking at partial hydrogenation. We had 1 hydrogen or we had 2 hydrogens. So typically selectivity is one of the most important aspects of a chemical reactor. And it's a flow reactor. One way we can define it is the flow rate of the desired product over the flow rate of the undesired product, where this is moles, say, per second leaving the reactor. So F representing a molar flow rate. The other way, if it were a closed reactor or a batch reactor that we'll talk about, it would be the number of moles of D over the number of moles of U. So this has units now, just total moles of product D. And why selectivity is so important is because it affects the subsequent separation of these 4 species, and separations is one of the most expensive aspects of reactors, plants. Also, if we react a lot of A and B to make a product U that we can't use, then we're really essentially throwing away some of our reactant that we have to buy. So the real purpose of the reactor is to take something that's less expensive, A and B, make a product D that's more expensive. And what governs behavior and what we're interested in for chemical reactors are mass balances and energy balance for the reactor and equilibrium, chemical equilibrium. So this, of course, affects how much product we can make. And the important thing that we use in these mass balances is rate of reaction. So we want to be careful in how we define that. So rate of reaction, we're going to use it as moles per volume per time. And this can have positive or negative sign. If it's, in this case, a reactant, it's going to have a negative sign, and it'll be a rate constant, which depends on temperature. And for example, let's say for the first reaction, the rate of reaction is first order in A and first order in B. Now, an important thing to keep in mind, this is not the same as the change in concentration of A with respect to time. In some special circumstances, that's true, but in general, it's not the case. If we're looking at this flow reactor that's a steady state, the change in concentration with time is equal to 0. So we have to be careful. Talk about rate of reaction that we're going to use in the mass balances. So let's look at types of ideal reactors that we're going to most commonly use. And sometimes these are good representations of real reactors. Sometimes real reactors are a combination of ideal reactors. So I'm showing here 4 types of ideal reactors. A batch reactor, which you could think of essentially as a laboratory beaker that's scaled up or mixing it. Then in general, of course, the concentration would change with time and temperature would change with time, right? So both of these in general will change with time. Continuous stirred tank reactor looks like a batch reactor where we continuously add, continuously remove material at steady state. So that means the concentration and the temperature in the reactor are both constant. They're not changing with time. Derivatives with respect to time are equal to 0 because it's steady state. A variation on batch reactor is a semi-batch reactor. And this can take different forms. In this case, I've drawn it where, for example, we start with A in the reactor and then we add B. And this means it's not at steady state. And therefore, like batch, both concentration and temperature can change with time. And then the final one we'll look at, plug flow reactor, which we can envision as a tube that we're flowing material through. It's again at steady state, so that means derivatives with respect to time are equal to 0. So the important thing, the concentration of A and the other species, of course, and the temperature, they change with location. In other words, if we consider this volume our variable, as we move down the reactor here, volume is 0. Here is our total volume. As we move down, Ca reacts, Cb reacts to form products. So these three reactors, when we model them, we assume that they are uniform spatially, or the other term used is they're gradientless. Now if we look at the mass balances for these, for the batch reactor, change in number of moles, so A is the number of moles of A, respect to time is the rate of reaction times the volume of the reactor contents. And in that case where volume is constant, the number of moles, of course, is the volume times the concentration. So you can see it's independent of volume if the density doesn't change. CSTR, steady state, the mass balance is the molar flow rate entering, so FA0 here, this is the molar flow rate leaving, minus FA plus the rate of reaction times volume. Semi-batch reactor can take different forms depending on exactly how we're running it. The general form was we have a flow rate in of A or B. I'm just writing the balance for A now. Flow rate out, which may or may not exist, and rate of reaction times volume. And then the plug flow reactor is the change in the molar flow rate as a function of cumulative volume as we move down the reactor, and that's equal to the rate of reaction. I won't talk about the energy balance here. I'll just mention one other term that's commonly used, and that's conversion, where if we look at a plug flow reactor, conversion would be flow rate in of A, flow rate out divided by the flow rate in. So this is a fractional conversion. This is also the case for a CSTR. That's both of these are steady state. For a batch reactor, it would be number of moles of A we start with, number of moles later time over the number of moles of A that we start with. And for semi-batch, we have to be pretty careful that conversion may not be a good variable. So this is just a brief overview of ideal reactors and their mass balances.